Finally, I want to work through two complete integration problems where we have to start with the partial fraction decomposition. We've got to check to make sure we have proper fractions. We've got to solve for our arbitrary constants, and we're not done until we've actually found the antiderivative as well, because that's our ultimate goal here. These problems are not going to say use partial fraction decomposition. They're just going to say integrate. So we have to be able to recognize when we're working these problems that we should try partial fraction decomposition. And the one thing that we can look for when we're working these problems that will help us to identify that we should try partial fraction decomposition is that we have a rational function and we can factor the denominator into simpler pieces. That's always a good indicator that we should use partial fraction decomposition. So the first one we're going to try is 2x cubed divided by x cubed plus 5x squared. So we have not seen an example of this yet, but this one is not a proper fraction because the degree in our denominator is not larger than the degree in our numerator. They're actually equal. So what we need to do first is polynomial long division to get this simplified. The only thing in our dividend is the 2x cubed. We could add 0x squared plus 0x plus 0 if we want to. Because our powers match, I'm only going to be able to do one round of division. Remember, when you do polynomial long division, the first step is to divide, and when you divide, you only compare the first term of each piece. So we're trying to figure out how many times x cubed will go into 2x cubed, and that is twice. Because when we multiply down and subtract, our goal is to have that piece cancel completely. So now that we've figured out the division part, we're going to multiply down and subtract. 2 times x cubed is 2x cubed. 2 times 5x squared is 10x squared. And we need to subtract this stuff from what we already have. And we know we did polynomial long division correctly if those first two terms cancel away. Now, I don't have any squared terms to take that 10x squared away from. That just means we have 0 of them, and if you want to, you can say 0. So we're left with negative 10x squared. And we can't divide any further because now our power is smaller than what we're dividing by. So that's actually our remainder. So we write our remainder as a fraction. So because it's negative, I'm going to say minus 10x squared over x cubed plus 5x squared. Now we have a rational expression to work with. We now have a squared in the numerator and a cubed in the denominator, so it is now rational. The 2 is still a very important part of the integration problem. We still have to consider the antiderivative of 2 when we go back and finally do our integration. But for the partial fraction decomposition, all we need to worry about is that piece. So I'm just going to pull that piece aside, and we're going to talk about how to do the partial fraction decomposition for 10x squared divided by x cubed plus 5x squared. It's now a proper fraction, so we know we've got to start with factoring. So we can pull x squared out, and if we do that, we're left with x plus 5. And you should notice that we have an x squared in the top and an x squared in the bottom, and they will actually cancel, which is very helpful. So really, this is just 10 over x plus 5. Much simpler. that's already linear denominator. We can't break that down any further. All we can do is go back to our 2 and say minus 10 over x plus 5. So doing that polynomial long division and also recognizing common factors is very, very important part of the simplifying process. So once we did those 2 steps, what we're left with is 2 minus 10 over x plus 5 that we want to find the antiderivative for. And because I now have them in 2 separate terms, I'm going to integrate them individually. The antiderivative for 2 with respect to x is just 2x. And then I've got minus. And now for this piece, anytime you've got a linear denominator, it's going to turn into a log. You should write out the u substitution just to make sure no new coefficients are introduced, but you're always going to let u equal your denominator. So u is x plus 5. du, the derivative for u equals x plus 5, du equals 1 dx. So du just equals dx. That means there's not going to be any additional coefficients introduced to this problem. The coefficient that we have originally is our numerator, which is a 10, and that's going to stay the coefficient in the problem. But what that's going to end up looking like is the integral of 10 over u du, which is 10 natural log of u. And if we scoot that back up here and replace our u, we have minus 10 natural log of x plus 5 plus c. So we didn't even have to do any partial fraction decomposition on that one. Once we did the polynomial long division and recognized some common factors, it was ready to integrate. But it's a good thing to note that when you have those linear denominators, the antiderivatives are always going to turn into logs. So I'm actually going to go back. Okay, I did call it A. So let's look at another one that's not going to be quite as simple that we will definitely have to do partial fraction decomposition for. This time we are going to integrate 4x minus 2 over x minus 1 times x squared plus 4 dx. And this denominator is already factored for us, which is actually helpful. To recognize that you need to use partial fraction decomposition, we're going to see a rational expression in our integrand, and we will have a factorable denominator. So we're ahead of the game already here because it's already factored for us. I'm not going to worry about the integration part just yet. We'll come back to the integration once we have this guy split up. Right now, most of the work is just going to be algebra, figuring out how to split up the 4x minus 2 divided by x minus 1 times x squared plus 4. Now these are already factored. We've got one linear factor, and we've got one quadratic factor. So linear factors get constant numerators. Quadratic factors get linear numerators. So that's our basic setup. To start solving for our arbitrary constants a, b, c, remember we're going to multiply through by that original denominator. That will clear our fractions. Going to multiply all 3 fractions by it. It will completely cancel off the original denominator since they match, and we'll just be left with 4x minus 2. In our a fraction, the x minus 1's cancel, so we're left with a times x squared plus 4. And then in that last fraction, the x squared plus 4's cancel, so we're left with bx plus c times x minus 1. Because we have an irreducible quadratic, we might just want to go ahead and get the right-hand side all foiled out and then just match up like terms. That might be the easiest way to go here in figuring out the a, b, and c. We're not going to be able to find magic numbers for zeroing out x squared plus 4. So if we get this thing all multiplied out, we get 4x minus 2 equals ax squared plus 4a plus bx squared minus bx plus cx minus c. And I'm going to go ahead and I'm going to match up like terms on each side. I do have some squares in here, so I'm going to start with squares and then work my way down. Do linears and then constants. So for my squared terms, I don't have any of them on the left, so the coefficient would be 0. On the right, I've got a plus b. For the linear terms, I've got a coefficient of 4 on the left, and then I've got negative b plus c on the right. For the constants, I've got negative 2 on the left, and I've got 4a minus c on the right. This one's not quite as simple as the last one we saw like this. The last one we saw, we were very easily able to solve for one of our unknowns in one of these equations and then use it to work backwards. But all of these equations have 2 unknown values in them. So because we still have 3 unknown values, a, b, and c, you could think of this as a system of 3 linear equations with 3 variables. So I'm going to rewrite this as 1a plus 1b plus 0c's equals 0. That's the same thing as what I have here in my first equation. There's 1a and 1b and no c's, and I had it equal to 0. And I'm going to do that for all my equations. I want to know exactly how many a's, b's, and c's I have. So my second equation has no a's, a minus 1b, and a plus 1c, and it's equal to 4. And then my last equation has 4 a's, 0 b's, minus 1c, and it was equal to negative 2. Now the fastest way to solve this is in your graphing calculator. You can type it in as an augmented matrix. An augmented matrix is when we type in all of those coefficients and the solutions and ask the calculator to solve it for us. So that's why I wrote out how many a's, b's, and c's every single equation had, and I made sure that they're all in the same order. So my first column in my matrix is going to be the a's. My second column is going to be the c's. My third column is going to be the c's. And my final column is going to be those solutions, what they're equal to. So this matrix is going to be 1, 0, 4, 1, negative 1, 0, 0, 1, negative 1, 0, 4, negative 2. So what we have here is a 3 by 4 matrix. And we can type this 3 by 4 matrix into our calculator and ask the calculator to figure out the reduced row echelon form. Of the matrix, and what that's going to do is it's going to solve it for us. So in the calculator, it's RREF. So the first thing we want to do is store this into our calculator under matrix. So you have a button on your calculator that says matrix, and then there's some options when you go into the matrix screen. Matrix can actually be found by hitting your second function button and then x to the negative 1. If you look at your x to the negative 1 button on the left-hand side about halfway down, you'll see matrix is written right above it. So if you go into your matrix screen, there's 3 lists of options. The first option is names, and that's just where you recall matrices that you've already created. The second option is math, and those are some different matrix specific calculations. If we just want to multiply, divide, add, subtract, we can do that with the regular buttons on the calculator, but there are lots of other calculations we can do with matrices as well, and that's what we'll find under math. And then the last option is edit. That is where we enter a new matrix. So that's where we need to start, is on the edit screen. So when you're on your matrix screen, if you arrow over to the edit list, you're just going to see a giant list of letters. And these are just different places where you can store your matrix. As long as you don't have a matrix already in there that you're trying to save for something, the easiest thing to probably do is just put it in matrix A, which is option number 1. So I'm going to hit option number 1 under edit, and I'm going to put my matrix in as matrix A. You need to tell the calculator what size matrix to create for you. And we have a 3 by 4. That's because this thing has 3 rows and it's got 4 columns. So right away it wants to know what size matrix we're going to create. And when we tell it how big, it will create enough spots for us to enter all the numbers that we have. So now we should see a 3 by 4 table where we can enter all the numbers from our matrix here. So I'm just going to start entering these values. 1, 1, 0, 0. And when I enter them, I just like to go across the rows and hit enter. And enter will automatically move me to the next spot in the row. And then I'm down to my next row, 0, -1, 1, 4, and then 4, 0, -1, -2. Now be really careful, make sure your matrix is entered correctly. It's always a good idea to double check your matrix before you leave the screen. If you have just one number entered incorrectly, your answers will come out completely wrong. Once you have your matrix entered, you need to go back to your home screen. Just completely quit out of the matrix screen and go back to your home screen. Otherwise, it's going to think that you're continuing to edit your new 3 by 4 matrix. Now that we have that matrix stored, I'm going to go in and I'm going to ask the calculator to do row reduced or reduced row echelon form on matrix A. So I'm going to go back to my matrix screen, and this time I'm going to go to math, and I'm going to scroll down until I see RREF, which on my calculator it's option B. So you got to go through 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it says 0, A, and B because there's so many options in that list. So scroll really far down in your math list, and option B is RREF. If you select that, all it's going to do is it's going to put it on your home screen. We need to go back into matrix again, and under names, we need to tell it which matrix we want the reduced row echelon form for. So now under names, I'm just going to choose A, and you should see next to A it says 3 by 4 now, because that's where we stored our 3 by 4 matrix. So this is exactly what I see on the home screen of my calculator. And I'm going to hit enter, and they give me back another 3 by 4 matrix that says 1, 0, 0, 0.4, 0, 1, 0, -0.4, 0, 0, 1, 3.6. This last column are our solutions, and they're in the exact same order that we put our variables in the columns in the original. So I originally ordered them A, B, C, which means these are going to be A, B, C. Another way you can tell if you put your little labels on the top. So follow A down to where it has a 1, and wherever it has a 1, you can follow it across to its answer. you can follow B down to where it has its 1. Or wherever it has its 1, you can follow it across to its answer. And then follow C down to the 1, and then follow it across to the answer. So what reduced row echelon form does is it always creates these zeros and ones at the front of the matrix and then gives the solutions at the back of the matrix. If you want to, you can change these to fractions the same way you change any other number to fraction. So you can just hit Math option 1, which says answer change to fraction, and it will give you back the exact same matrix again, but it will give you those numbers in fraction form. So now it says 1, 0, 0, 2 fifths, 0, 1, 0, negative 2 fifths, 0, 0, 1, 18 fifths. Now you may have learned in algebra class quite a while ago how to solve these 3 by 3 or 3 by 4 matrices by hand, or these, actually probably the better way to say it is solve these systems of 3 equations with 3 variables by hand. And if you remember how to do that, that's perfectly fine. For me, it's just faster to do it with a matrix and just do it in the calculator. That way I don't make any silly arithmetic mistakes. So now I've got my A, B, and C values. So we know that the basic setup for our partial fraction decomposition, let me remind myself of my denominators. We had a over x minus 1, and then bx plus c over x squared plus 4. So 2 fifths over x minus 1 plus bx plus c over x squared plus 4. These two fractions added together are equivalent to the original fraction they gave us, except integrating these two fractions individually is going to be easier. Now I did say earlier that when we had those irreducible quadratics, we're actually going to want to split them apart. So we're really going to have 3 fractions here. 2 fifths over x minus 1, and I'm going to change that to subtraction for this one, minus 2 fifths x over x squared plus 4, and then plus 18 fifths over x squared plus 4. And now this one's going to be even easier, because the one with the linear denominator is going to turn into a log. The second fraction that had a squared in the bottom and a linear in the top, that one is a perfect setup for a u substitution. And then this last one that has a constant in the top and a sum of squares in the bottom, this one is going to turn into tangent inverse. So just look up your formula for tan inverse and follow that formula. It's pretty easy. So when we integrate, this is going to turn into 2 fifths natural log of x minus 1. If I set up my u substitution for my second fraction, I'm going to let u equal x squared plus 4. du is going to be 2x dx. So 1 over 2x du is going to be dx. So I've still got minus the integral of 2 fifths x over u times 1 over 2x du. Now those x's cancel. We could put the 2 fifths divided by 2 together in the front, and that's going to make 1 fifth. And we see that this one's going to turn into a log as well, because we just have the integral of 1 over u. So now we've got 2 fifths natural log of x minus 1 minus 1 fifth natural log of the u for the second equation, which was x squared plus 4. And now we need to figure out how to do this last one. This tan inverse integral formula is on page 324 in our textbook. But actually, I've got a nice kind of consolidated reference sheet with a lot of important trig identities and basic derivatives and basic antiderivatives that I'm going to post for you as well. It might be a lot easier for you to just print that off and just reference that whenever you need that, instead of constantly fumbling through the book to try to find the things that you need. But I'm going to go ahead and write it here for you. On page 324, it says the integral of 1 over a squared plus x squared dx is equal to 1 over a tan inverse of x over a plus c. So this piece right here is a sum of squares. The a is just a number and the x is our variable. The way that I know x is the variable is because of the dx at the end of our integral. So if we compare that with what we have, our a value, if 4 is a squared, that means we have an a of 2. Our 18/5 is just a coefficient. So for this piece, I'm going to have 18/5 that just automatically is going to come down. And then the formula says do 1 over a, so I'm going to have 1 over 2, and then tan inverse of x over a, which is going to be x over 2. So then that's going to turn into 9/5 when we simplify. 18/5 times a half is 9/5. Tan inverse of x over 2 plus c. That's about as difficult as these are ever going to get. It's a lot more likely that you're going to see just factors that are just simple linear denominators and they're all going to turn into logs or things like that. Or we'll have repeated factors where we just have to do a simple u substitution for whatever is inside. But the most difficult are when we have these irreducible quadratics and we have to separate the numerator and then it turns into even more pieces to integrate. Again, the linear denominators always turn into logs. When we separate that quadratic factor, the piece that has the linear numerator, we do a u substitution. That one also turned into a log. And then the last one where we had a constant over the sum of squares, that one was the tan inverse formula. And I'm going to go ahead and post this reference sheet with all of these derivatives and integrals and trig formulas. That way you have just one nice place to look for everything. It'd probably be a good idea for you to go ahead and print it off and keep it with your notes for this chapter. That way it's nice and handy when you take your test as well. You can also maybe star the formulas that you find yourself using most often. That way you're not having to search and remember which ones to use. So that one was really, really tricky. You're really not going to see anything harder than that one. So just to take a step back really quickly, I want to do an easier one. I don't want to freak you out and think they're all going to be that difficult. So we're going to do one more. This time we're going to integrate 2x over x squared minus 3x minus 10. Same type of problem. We've got a rational expression we're being asked to integrate. U substitution's technically not going to work here because if you let u be equal to your denominator, the derivative is 2x minus 3, and we don't have a minus 3 in our numerator. So even though the two x's match up, anytime we've got terms attached together with a plus or minus, we cannot break them apart and cancel just pieces of them. So u substitution is not going to work here. But that denominator is factorable to x minus 5, x plus 2, which means I'm going to be able to break this up into just two nice, simple, linear fractions. Oops. That should be a minus 5. And then remember what linear denominators integrate to. We had a linear denominator here. It always just integrates to a log. So I've got two different linear factors. They're each going to get their own fraction. and because they're linear, their numerators will be constants. We'll go ahead and multiply through by that original denominator on all three fractions. And after we cancel everything we possibly can, we'll be left with 2x equals a times x plus 2 plus b times x minus 5. Now remember, with these linear factors, we could use that magic number method. So I'm just going to plug in some x values. If I use x equals 5, the b term's going to zero out, and we'll be able to solve for a. So I'm going to go through and replace all my x's with 5s. And that's going to give me 10 equals 7a. The b term zeroes out because I have 5 minus 5. So my a is 10/7. Now to zero the a term out, we're going to use x equals -2. And if I plug -2 in for all my x's, I get -4 equals -7b. The a term zeroed out because we have -2 plus 2. So b is just 4/7. So now we're ready to rewrite our integral as two separate fractions. So the a was over x minus 5. So we're going to have 10/7 over x minus 5 plus 4/7 over x plus 2. And both of these are just going to integrate to be natural logs. The numerators are just going to come out front as coefficients. It's a good idea to write the u substitution out just to make sure that no extra coefficients are going to be brought back in when we change it. But here, if we let u equal x minus 5, we just get du equals 1 dx. So an extra coefficient of 1 multiplying by 1 doesn't do anything. And here, if we let u equal x plus 2, du equals 1 dx. So nothing extra. So we can literally just jump to our answer. So much, much simpler. That's a much more typical problem. But I always want to make sure I show you a difficult one. That way you can see all the methods that could possibly be used.